Yeah. So even before we go, oh, so even before we start doing the uh, basically Turing problems, what one should ideally check first is whether we are able to do the simple diffusion equation problem. So what we'll do is just first look that if you start, so suppose you have a lattice which is 60 cross 60, and here though I have written down the diffusion constant of A and diffusion constant of B, and the alpha and beta parameters corresponding to the Fitzo Nagumo parameters. So what I'm going to do is start with suppose you have an old temp A, and just in the middle of the box you have placed a droplet. So here it is zero point 0.0. So the density of suppose you're solving the diffusion equation where the variable you are solving for is the density. You want to see if you put a droplet in the center of the box, how it diffuses out. Okay. And basically, since we are using the explicit method, we should choose a small value of dt, which you have chosen to be 0.01, and dx equal to 1 and dy equal to 1. Okay. And yeah, so this is the problem, and we want to be sure that it is diffusing out correctly. And I've set this to be, let's start with diffusion constant suppose equal to 1. Okay. And how does it diffuse out? Furthermore, I am saving a snapshot of 100 iterations, and the total number of iterations is 2000. Okay. So I'm going to run this in a 60 cross 60 lattice, and there's a droplet at 1.0, and let's see whether what kind of droplet diffusion do we get. So this is the compiled version. Here I'm diffusing it. Note that only one point in the lattice does one have a droplet, a density equal to 1 at the center of the box. And as the particles diffuse out, what I have written out is the total number of, if you like, the sum of density, the sum of particles spread over all lattices, and that is 1. And that's a cross check, and that's an important cross check, right? Now, let's see how it would look in octave. Okay, so I have written also a suitable code in octave where I have added all the thing. There is basically a slight modification of the Ising model code, and access is 0 to 61, and after each snapshot there is a 0.25 pause so that we can properly visualize it, right? And there are 20 snapshots because I'm saving data every 100 iterations, and the total number of iterations is 2000, right? So these are the parameters. Now if I basically plot the movie, now you see that at time t equal to 0, there was a very bright spot. I think you didn't get to see it, and it has diffused out all over the lattice, right? So that's what you're seeing. And now suppose I want to slow it down so that you can see what happened initially. So what I'm going to do is have a pause of 0.5 seconds, and the c-axis, which is the range of that axis after thing has spread out. At the moment, it's 0.05, but let me do it. Uh, yeah, but so remember, so now this is the upper limit. This is the upper limit. So even if at time t equal to 0, at one point the density is 1, right? That will be set to this maximum value of 0.05, and that's how we will plot it. So let's have a look again of how this looks, and this is domains. So you see that there was a yellow spot and that is slowly spreading out, and over the time, over 20 snapshots, 2000 iterations, it is basically become uniform, right? And here you see 0.005, and you can hardly see the blue color. Now, what happens if I change this to say uh, 02? Okay, here we have not changed the calculation data. It's only that we have changed the plotting data, right? And let's see what happens is with this yellow color, and then this is blue, and you see this is spreading out gradually, and that's what diffusion equation is supposed to do, right? And that's what you get, and here you see a slightly more bright blue, I mean, compared to the previous ones. Now, suppose we have higher density. Instead of 1, I put 5 here, right? Let's, if I put 5 here, so at time t equal to 0, so this is the beginning of the run, I have a higher density. It will spread out, but how will it look different? Just let's, you have to run it. And now the sum of the density across the lattice, which is a cross check, is 5. And now let's just look. It starts with yellow as usual, but now this is spreading and it remains yellow because the maximum range of colors that I have given is a 0.05, right? So the more particles spreading, you can see a brighter spot. So even after 2000 iterations with dt equal to 0.01, you see that there's a bright spot here. Gradually, what has happened if you run it for a longer time, or increase the diffusion constant, or increase the dt, uh, eventually the density will be uniform all over the lattice, right? So let's just check that. Let's just check. Suppose we choose dt equal to zero point zero 0.02. I have kept the density same. So basically, all that will happen is uh, in 2000 iterations, it would have run a longer time because your dt is larger, and total number of time evolved is dt into number of iterations. So you have a longer time evolved. Okay, so let's see what's the consequence of that. Let's compile. That's it's 5000. Sorry, 5. Still the density. Now, though the number of snapshots is exactly the same, the amount of evolved time is more. And what you see is basically that the thing is spreading out, because last time it was yellow, but now 2000 iterations, but a longer time because dt is more, there's no yellow here. It has more uniformly spread out. Okay, fantastic. But now if we decide to have two droplets, we can have two droplets because, just one droplet, you cannot even do it analytically, how it diffuses out. Of course, you can quantify what can you quantify? You can quantify the spread with time, with the diffusion constant. You know how much the spread should be as a function of time. Does it match? But you can do all that. But let me suppose switch on two droplets, not only at suppose. So I'm introducing a droplet at 1 by 4 of the lattice, Lx by 4, Ly by 4, and then one more at 3Lx by 4. So it's diagonally off. And let's have a different value of the thing. So let me have this at as 5, and this is 3. So there's less amount of material, lower density if you like, within that square box for this 3Lx by 4 and 3Ly by 4, which is basically 45 at 45. So this is of course 15, 15 and 45, 45. And now we can see two different droplets of different size density actually spreading out. So how would it look? Let's try to visualize it. Now look, it's 3 plus 5 equal to 8 is the total amount of conserved mass. And if we try to visualize it, uh, now you see there are these two domains. I don't know, of two different. I thought one should be 45 and the other should also be 45. So I have to check what mistake we just did. Ah, so this is Ly by 4. Okay, so let me put it at 45 cars, 45, and let me run it again. Yeah, so let me make this movie again, and let's see how it. We have two different droplets at two different points, diagonally situated, and this is how it spreads. And remember, one of these points had lesser amount of liquid, and now you can see how two droplets uh, vary. Okay, now if we increase the diffusion constant, then what would happen? Let's increase the diffusion constant. Then, well, you can guess what will happen. It would most probably spread faster. Uh, does it match our intuition? So let's run it. I'm keeping the amount of mass same so that at a time I want to change just one variable. What happens? Ah, so compared to the previous case, there is a periodic boundary condition, and you can check for yourself that it has spread out more in the same time. Here you can hardly figure out. It has almost become this indigo blue, right? Here you can still figure out that there was some. And this is basically mass spreading across, right? It's becoming more uniform, right? Now let me introduce two more droplets. Why not? And see, now we can see the competition of different droplets, and of course I had already tried this out before. So let's put 5, 5 3 5 7 and 10. So where are these? So these so this was of course at 15 15. This is at 45 45. Here I've put it lx by 4 and 3ly by 4. So that's something like this is 15 and this is 45 and this is again 45 45. So I will put it I think I'll put it lx by 4. Ah, yes, so there should be four droplets at four different points, right? This was 3ly by 4 and lx by 4. This is 3lx by 4 and ly by 4. There are four different droplets of four different sizes. And now let's see what happens. Diffusion.com. Sum. Sum is 25. Does it match? So the total density was 5, right? Plus 10, 15, 7 plus 3, 10, 25 matches. So let's see how these four droplets now diffuse out, right? Uh, and now you see that it is really becoming uniform over the entire box. Remember, this range is zero point zero 0.02, right? And this will look, so basically the average density all over 60 cross 60 lattice sites is approximately close to 0.01, corresponding to this color. Now if we had let's do two things. Suppose let's change the total number of iterations to 4000. Okay, so that's one thing I did. I put back the dt equal to 0.01. And if I put down, so basically now you're running it for the same time, they're running it for the same time, but you have more snapshots, right? So you're saving snapshots every 100 iterations. So you're having more snapshots over the same time. Why? Because they doubled total number of iterations and decreased dt. The other thing that I'm going to do is also change the c-axis value. So ideally, you should be getting an identical picture, right? So let's see, except that it will be over a larger number of frames. Now to run it also. Okay, yeah. So you have more number of iterations. Now also this code, the plotting code should be able to handle larger number of snapshots. Previously it was handling 20 snapshots. Now it should handle 40 snapshots. And we should be getting a picture very identical to that, except after 40 snapshots. Let's see whether that works out. Of course, it has to. Uh, except now in each year, making a snapshot after more frequent intervals, right? So it's after 40 snapshots that it will reach the same time. And you see it slowly diffusing out. It's becoming relatively uniform. One can hardly see any difference. All the density has. Now, if I change this back from zero point zero 0.02 to zero point zero 0.05, what would happen? Let's do that. Let's change it to say 0.03, 5. I've changed nothing else. I've not changed anything in the code, so I don't need to compile or run it. But how would this look different? Is the question I'm asking. It will become deeper blue, right? Because the range, we have increased the range of the thing. So domains, let's see what happens. So it's a deeper blue because the range is more. The data is the same. I didn't run it, right? It's basically here, zero point zero 0.01. So some color like this here. There's a large droplet. So you can still see some very light blue. But the rest, it has diffused out and tried to become uniform. Now, now suppose, uh, uh, so here we started with 4 droplets, but suppose at a certain point in space, we add liquid. As the simulation goes on, as the system tries to diffuse from the initial condition all over the lattice, suppose there's a pipe at somewhere at 1515, say, and we keep adding liquid at 1515. We can't add too much, but because you have to get your integration right also. But suppose let's add a source term, and we add a very small amount of liquid. We add a very small amount of liquid, mm, right from the beginning. Uh, let me, yeah, okay. Let me add a small amount of liquid. So I'm adding two amounts of liquid at two different points. Let me switch this off. Let's keep it simple. Let's add a small amount of liquid as we go along. So in every DT, a small amount of thing is being added and being updated. So how would this look? So all that I've done here, just to give you the idea, that normal diffusion process is going on. But as the number of iterations is going on here, right, I'm updating old temp A, because old temp A is being used to calculate temp A. I'm updating that and adding a small amount of liquid density, density of the fluid, at is only a local point in space. Of course, I could have added it to multiple spaces, or I could have just added it to, I don't know, somewhere else as well. Uh, but let's see what happens. Uh, how does the movie look? So here I'm adding liquid, and you see the amount of material is not conserved anymore because I'm constantly adding liquid. Previously, it started at 25 or something like that and remained constant. Now I'm adding liquid. So the consequence of that will look like this. Now see, every point is diffusing out except here. Since you're adding liquid constantly, though this is also spreading out, but constantly liquid is being added, and hence it maintains M. yellow spot, right? So that's the consequence of 40 droplets of liquid. And even at the end, I mean, end of the simulation, not end of the diffusive process, is a bright yellow spot. Now, suppose let's change it and put it to middle of the box. So suppose I'm including some liquid only at the middle of the box. Okay, and very gradually keeping on adding liquid. Lx by 2, Ly by 2. So I'm adding some liquid at the middle of the box. And whereas rest of the initial four droplets are diffusing out. How would you do that? Again, of course, total amount of mass is not conserved. But if you had to plot this, then this is how it would look. So these are all diffusing out, whereas here the concentration is gradually increasing because you're constantly adding matter to the system, right? So that's what happens. So now there's a time dependent. Rest of all the things have diffused out, but here there is still matter which is being added and which is constantly diffusing out. If we increase the diffusion constant, let's see, increase the diffusion constant, oh, or let's decrease it. Let's decrease it to 1, say. And this was the size of this droplet. The amount of matter which is going to be added will be the same, but the size of the droplet or the diffusion will be different. It's going to go get slower. Does it match our intuition? At least pictorially, quantitatively also you can do. Yeah, the same amount of matter is being added, but when one does this, you'll see the entire diffusion process becomes slower, though the amount of matter being added is at the same rate. Now, now this one has nearly disappeared, but you can still figure out the consequences of these two. In this one, oh, okay, there is a higher concentration because this is 0.05. Things have been unable to diffuse out, and hence you are seeing a bigger droplet. Suppose you make the liquid addition itself time dependent, which means that only after suppose number of iterations has crossed is greater than suppose 999, you start adding liquid. Everything else remains the same, right? So now you have four droplets. You're adding liquid at a certain point in time. There's a source term, so the total amount of liquid which is diffusing out is not conserved. Moreover, you have an added a time dependence even to the point. So only after 1,000 iterations have you started adding liquid. So slowly, gradually increasing the complexity, right? So let's see what will happen. Of course, we have again. So previously it was going up to 45. Here you started adding liquid after a later point in time. As a consequence of which, uh, yeah, so as a consequence of which you have added less amount of liquid over the whatever 3,000 equations or so. And then if we do domains, you see there is no central liquid being added here, but after some time, some yellow droplets start appearing here and start diffusing. So this is a time dependent source term, and we can play with all of this as we wish, right? So it's basically here that I shall stop the diffusion modeling of diffusion, pure diffusion equation of one species, but now add some nonlinear term and see the consequences of that, which will be, yeah, so which will be. So basically, let me stop sharing, then let me stop recording.